The seventh step, it will be regarding the phase plot. Regarding the phase plot, as I mentioned, the phase plot for poles and zeros. Okay, the two factors, real poles or real zeros, whether they are simple or repeated, or the quadratic poles or zeros. They have a corner frequency of omega c, and the transition will take place between 0.1 omega c and 10 omega c. So here on the frequency plot, we should assign 0.1 omega c, okay, and 10 omega c for both poles and zeros. And again, we will label them as simple zero, simple pole, or quadratic pole. So at those frequency, okay, within the range of 0.1 omega c till omega c till 10 omega c, for if you assume a zero, it will have a slope of plus 45 q degrees per decade. While if we have a pole within the range of its corner frequency between 0.1 and 10 omega c, it will have a slope of minus 45 q degrees per decade, and the q is the multiplicity of the root. Okay, so by this mean we can construct and draw the frequency plot regarding the magnitude and the phase of the loop transfer function. Okay, this is the semi-log paper. What do we mean by semi-log paper? Semi-logarithmic paper means that the y-axis or the vertical axis is linear. It's linear. The displacement between the grid here on the y-axis is linear, while the frequency axis or the x-axis is logarithmic. Okay, so here it's linear and here it's logarithmic, and we should construct two graphs, one for the magnitude and one for the phase. One for the magnitude and one for the phase. So this will be the graph for the magnitude, the higher one, okay, and the next one will be the graph for the phase. So this is the graph of the phase, okay, plot, and this one is the graph for the magnitude plot. So here, as I mentioned, that assume we have, I will enlarge it. If you pay attention to the logarithmic, to the frequency axis, okay, so it's logarithmic scale between 1 and 10, it's logarithmic. The displacement between 1 and 2 is larger than the displacement between 2 and 3. And as we move toward the decade 1, which is 10, the separation is smaller. And this is the first decade, this is the second decade, and this will be the third decade, and so on. So this graph in general, it has, if you pay attention, if we have a look at it, this graph, okay, this graph has, this is the first decade, this is the second decade, this is the third decade, fourth decade, and fifth decade. It has 5 decades at the frequency axis. Similarly for the frequency and for the magnitude and the phase plot. So they have 5 decades. Okay, so we start, assume that we have like any random transfer function. I will assume it assume that we have a corner frequencies. Okay, we have a 0 at 1, simple 0 at 1, and simple pole at 3, and quadratic pole at 7, and simple 0 at 10, and simple pole at 15. So they are sorted. So what's the lowest corner frequency? It's this. And what's the highest corner frequency? It's this. So how to draw it? I will draw those regarding their magnitude on this graph, which is originally for the phase, but I will draw it on the phase, on the this graph on this paper. Okay, so we will start our graph with point 1, the lowest, which is equal, the lowest is 1. So we will start with 1 and we will end with 150, 10. So here, this frequency will be 0.1. This one will be 1. This one will be 10. This one will be 100. Okay, and this one will be 1000. Okay, so we will start our graph at 0.1, okay, and end it at 150. 150 will be approximately here, between 1 and 2. Okay, 150 is in this area. So assume that the system type n is equal to 1 and k, the gain is 1 or is 10. K is 10. So okay, how we will draw it? So we will label the initial slope of the graph will be the slope due to the system type, which will be minus 20 dp per decade. Okay, and this value will depend on both the gain k and the system type. We will specify it later. Okay, so we will continue in movement till we reach this one here. After that, so what will happen? We have a 0 at 1. So 0 will add plus 20. So this means that between 1 and 3, the next pole, between 1 and 3, 3 is here. Okay, it will be flat. And it has a 0 dB per decade. After that, after that, the effect of this pole will take effect. And this will add minus 20. So again, we will have minus 20 between minus 3 and between 3 frequency and 7. So between 3 and 7, this is 7. We will have minus 20 again. Okay, so this is covered. Till we reach till we reach 7. Now from 7 till 10, the effect of this quadratic pole. This means that we will have, or repeated pole, we will have minus 40. So between 7 and 10, we will have minus 40. And this is the 10, and this will be very steep, like this, with a slope. So this minus 20, this is 0. This is again minus 20 dB per decade. And this will be minus 60. Okay, till we reach till 10. 10, it will be the effect of the 0. 0 will add between 10 and 15, like here. It will be minus 40. It will be minus 40. This will be minus 40 because the 0 will add plus 20. And finally, when we reach to 15, this will be the effect of the simple pole. It will add again minus 20, which means that it will go with minus 60 for all frequencies higher than this. So again, it will be minus 60. So in this way, we can construct the phase plot. But the magnitude plot, sorry. But for the phase plot, how we can construct it? We can construct it by assuming that we say our the first one was a 0 at 1, I think a 0 at 1. So between 1, okay, between 1 and 100, this will be, it will be the effect of the first zero. It will be plus 45 degrees per decade. And I don't remember the exact number which I draw. Assume that we have a pole at 3. So from 3 to 30, it will be minus 45 degrees per decade. Then assume that we have, so this is 0.1, this is 1, okay, this is 10, this is 100, this is 1000, okay, around 10. So assume that at a frequency of 5, which is here, we have like a complex conjugate root, complex conjugate pole. So from 5, the omega c is 50. So from 0.1, the omega c, which is 5 till 500, it will be the effect of the complex conjugate root pole, which will be minus 90 degrees per decade. And assume that at the frequency of 70, there is, okay, the effect between 70, okay, and 7,000, okay, the effect of a zero that will add plus 45 degrees per decade. So what will we do now? We will segment this graph into parts. The area where any slope come out or go out, it will be calculated, and the slopes will be added. And for each segment, we will add the slopes of the above case. For this, we will add the slopes. For this, we will add the slopes. Okay, for this, we will add the slopes of the above. Okay, till we cover all of the transition period. Okay, after covering the transition period, okay, what will happen regarding the initial and the final for the magnitude and phase? So, regarding the magnitude plot, I said that we will start at certain value in dp and a certain slope. This slope is minus 20n, and n is the system type. And the value here is 20 log k, because k is there, okay, minus 20 n log 0.1 omega cl, the lowest corner frequency. So this is the value here at the starting value, the vertical value. And after that, the corner frequency will come like this flat. They will move according to the corner frequencies. This is regarding the magnitude plot. The phase plot, we will start the phase plot with a certain DC value, and this DC value will be minus 90 n degrees, constant. And after that, there will be movement of plus 45, minus 45, plus 90, minus 90, until we reach to the final. And assume that we reach the final here. This final value will be, okay, minus 90 multiplied by n minus m. Okay, n is the number of poles and m is the number of zeros. So it will be minus 90 degrees multiplied by n minus m. And the starting will be minus 90 degrees multiplied by n, and these are DC. They are not slopes, they are constant values here and here. And within this range from 0.1 omega cl till 10 omega ci, there will be the transition of plus or minus 45 multiplied by any factor or 0. And regarding the final slope of the magnitude plot, after reaching for the magnitude plot, assume that this is omega c high. So the slope after this will be constant. It has certain value, the slope, and this slope will be minus 20 multiplied by n minus m dB per decade. So we have initial slope for the magnitude, that is here in the initial slope, minus 20 n, capital N, and the final will be minus 20 n minus m, which is the degree of the denominator minus numerator. Okay, and as I mentioned, this value will be 20 log k minus 20 log 0.1 omega CL. This is regarding the magnitude plot, the phase plot. We will start it with minus 90 n degrees constant, and we will end it with another constant value, which is minus 90 multiplied by n minus m. And within this period, there will be the transition of plus or minus 45 q degrees per decade. And within the magnitude plot, assume that this was the starting. Within the magnitude, okay, within the magnitude, this was the starting value. As I mentioned, this starting value is 20 log k minus 0.1 minus 20 log 0.1 omega minus 20 n log 0.1 omega CL, and this will be minus 20 n dB per decade. And when we reach to the final value, this final value, the slope after the final value, it will be here. This here will be 10 omega C high. The final value will be minus 20 multiplied by n minus m. This is regarding the magnitude. Regarding the phase, as I mentioned, it will be constant value. It will be constant value here. Then the changes according to the poles and zeros until we reach like this final value. This initial value is minus 90 n, and this final value is minus 90 degrees multiplied by n minus m. So this all what I can speak about the magnitude and phase plots. Okay, here I will cover all of the points that I have mentioned on the Simulink paper. I will cover it now. Regarding the magnitude plot, the gain at the lowest corner frequency, which is 0.1 omega CL, will be only due to two factors. The k, constant gain k, which will be their contribution, will be 20 log k, and the two poles or zeros at origin, which is minus 20 n log 0.1 omega CL. So only k and integrators will appear here. And the initial slope after this point, 0.1 omega c, as I mentioned, it's minus 20 n dB per decade. And the final slope after reaching to 10 omega c high, it will be, as I mentioned, minus 20 multiplied by n minus m. And the slope anywhere within the curve, it will be 0 or multiples of simple or multiples of 20 plus or minus 20 dB per decade. This is regarding the magnitude plot. Regarding the phase, the initial phase below the lowest corner frequency, 0.1 omega CL, will be minus 90 n degrees. And the final phase after 10 omega C high will be minus 90 n minus m. And the slope, okay, anywhere within the graph will be plus or minus 45 or 0. It will be 0 or multiples of simple or multiples of plus or minus 45. So based on that, we can construct the magnitude and phase plot by scanning all the poles and zeros as I mentioned, as I show you, and we will add the contribution of each individual k term as we move from 0.1 omega CL till 10 omega C high. And after that, we will come up with the phase and magnitude plot or the bode plot. And from this bode plot, we will determine 4 factors: the gain crossover frequency, phase crossover frequency, gain margin, and phase margin. How? They are shown in this figure. Okay, so this is the magnitude plot and this is the phase plot. Okay, so what are the four factors that I just mentioned? The first factor is omega g, which is gain crossover frequency. What's this gain crossover frequency? It's the frequency at which the magnitude plot crosses the 0 dB line. This is the 0 dB line. So the frequency at which the magnitude plot, this magnitude plot, crosses the 0 frequency, the 0 dB line, is gain crossover frequency. This is the first one. The second one is this, omega p, phase crossover frequency. What is the phase crossover frequency? It's the frequency at which the phase graph, okay, crosses the minus 180 degrees. So we have 0 dB line for the magnitude and we have minus 180 degrees line for the phase plot. Both of them, the magnitude when it crosses the 0 dB and the phase when it crosses the minus 180 degrees, those are very important frequency. This one we call it gain crossover, while this one we call it phase crossover. Okay, and at gain crossover frequency we go down and find this thing which is called phase margin. Phase margin is the difference in degrees between the magnitude or the value of the phase plot at omega g and the minus 180 degrees line. Again, phase margin is the difference in degrees between the value of the phase curve at omega g here and the minus 180 degrees. So this is the difference and this is called omega phase margin. And regarding the gain margin, we find omega g from the previous step, omega p, sorry, and we go up, and the difference between the 0 dB line and the value of the magnitude plot at omega p, this difference is called gain margin, sorry. So we have four parameters. The first parameter is omega g. The second is phase margin. The third is omega p, and the fourth is phase margin. Okay, so these are the four parameters that we should know. So if the gain of the magnitude plot at omega p was below the 0 dB line, and we find this gain margin will be positive and the system will be stable. So if at omega p the value of the magnitude plot is below the 0 dB line, the system is stable, this area is stable, okay, and the gain margin will be positive. While if we go above the 0 dB line, the value of the gain margin will be negative and the system will be unstable. Okay, so this is regarding the stability and the sign of the gain margin. If we are below the 0 dB line, it's positive gain margin and the system is stable. If we are above the 0 dB line, the gain margin is negative and the system is unstable. So this is regarding the gain margin. Now we will switch to the phase margin. Phase margin. If at the value of omega g, the phase of the phase plot is above the minus 180 degrees, then phase margin is positive and the system is stable. If the value of the phase plot at omega g is below the minus 180 degrees, like assume that this was the curve. So this will be, so assume that the curve was shifted down, okay. Assume that this is the curve, okay. So at omega g, we will go down. This will be the gain, the phase margin, and this phase margin is negative, and in this area the system is unstable, okay. Similarly, if we go up, if the magnitude plot was like this, and at omega p we go up, then let me make it larger difference in order to differentiate. If this is the magnitude plot and this is omega p, then we will go down, up, and this will be the gain margin. This will be the gain margin, and this gain margin will be negative, and the system will be unstable. So these are the facts regarding the stability and the value of the gain margin. If we are for the gain margin and the phase margin within this sandwich area below the 0 dB and above the minus 180, then both of them they are stable, and both of them they are positive. The system is stable and both of them are positive. If we go above this or below this, then the system will be unstable, and anyone that go below the minus 180, then phase margin will be negative, or it might go above the 0 dB, then the phase margin will be, the gain margin will be negative. So I wish that by this clarification, everything regarding the phase margin, gain margin, omega g and omega p is clear. Okay. So these are the notes on the body plot. As I mentioned, gain margin is the distance between the 0 dB line and the gain of L of j omega at the phase crossover frequency, and this is given by this equation. And in other words, what can we say about the gain margin? Gain margin, if we add positive gain to the system, then the amount of gain that can be added to the system such that the system will be marginally stable. I will discuss it in a few minutes. So regarding the phase margin, is the difference in angle between what? Between L of j omega at gain crossover frequency and the minus 180, and this is the value. And what's phase margin in other words? It's the amount of negative phase that can be added to the system to make the system marginally stable. Okay. Gain of crossover frequency is the frequency at which the gain is 0 dB. And phase crossover frequency is the frequency at which the magnitude or the angle of the plot is minus 180 degrees. Okay. And these nodes, they are very important. Regarding the stability condition, for stable systems, gain margin and phase margin, they should be stable. Both of them, they should be stable. So here, this and is very important. For stable systems, gain margin and phase margin, they should be positive. This means that both of them should be within the sandwich area, below the 0 dB for the magnitude and above the minus 180 degrees for the phase. Okay? For unstable, if gain margin is negative or phase margin is negative, here we are speaking about or. Any one of them, if it is negative, this means that the system is unstable. How? If like the magnitude plot is above the 0 dB line at omega p, then it's unstable. Or if the phase plot is below the minus 180 degrees at omega g, then it's unstable. Or both of them. So here we are speaking about or. And for marginally stable system, gain margin and phase margin will be 0. Gain margin and phase margin will be 0. Okay, so let me discuss the marginal stability. Assume that this is the magnitude plot and this is the phase plot. Pay attention that phase plot should start from DC value, constant value, and should end at DC value. While the magnitude plot, it's not necessary. It should end with a slope, except n is equal to m. If n is equal to m, it will be a DC. And it should start also, if n, the system type, is greater than or equal to 1, it should start with a certain slope. Okay, so at this case, here this is omega g. And it's at the same location as omega p. So here, omega g is equal to omega p. And at omega p, we calculate the phase, the gain margin, it's 0. And at omega g, we calculate the phase margin, it's 0. So gain margin and phase margin, for marginally stable system, they will be 0. And for this case, omega p and omega g, they are equal. Okay? Omega g and omega p, they are equal if they are, system is marginally stable. Marginally stable means gain margin and phase margin is 0. Okay? So let me discuss another possibilities for the gain margin and phase margin. So this is the magnitude plot and this is the phase plot. So here omega g and here omega p. So we will go up and find this, and we will go down and find this. So in this case, this gain margin is negative and this phase margin is also negative. So the system is unstable for both cases. Gain margin is negative and phase margin is negative. So the system is unstable. Okay? So these are some of the cases which we might like encounter in real life. Okay, so now let's continue. This note, okay, it's cancelled. I will not discuss. And if the gain plot, the next one, if the gain plot has line over the 0 dB line, this means that we have infinite gain crossover frequencies. And if the phase plot lies over the minus 180, this means that we have infinite number of omega p's. So what does this mean? How? Again, I will draw this is the magnitude and this is the phase. Assume that we have so if we pay attention to this segment and to this segment, in this segment, the magnitude plot is lying over the 0 dB line. And in this segment, the phase plot is lying over the minus 180 degrees. And what do we define omega g? Omega g is the intersection point. In this segment, in this case, the intersection point is not a point, it's a segment, a line, and we can take any frequency within this range, it's omega g, so infinite number of omega g's. And similarly, the intersection of the phase plot with the minus 180, it's the omega p. And since we have coincident segment of omega, the phase plot over the minus 180 degrees, then this means that we have high number of omega p's, and their number is theoretically, since we are speaking about real numbers, is infinite. So this is what do we mean by the previous note. Okay, so let us go to the next comment. It says that for proper transfer function, where n is greater than m, generally but not always, we have monotonically decreasing magnitude plot and monotonically decreasing phase plot. What do we mean by monotonically? Monotonically, that it's decreasing. It's not increasing. It might be decreasing or constant or zero slope, but it should not have any positive slope curve, any positive slope part. So both of them, they have negative slope or zero slope, but not positive slope. This is what we mean monotonically decreasing. So I will go back to the previous, this one, and discuss the things. Assume that we add a positive gain to the magnitude plot. What will happen to this? We are adding, if it's a positive gain in dB, which means that in normal scale it's greater than unity. Okay? If we add a positive gain in dB, this means that the magnitude plot is shifted upward. Okay? And if it is shifted upward, what does this mean? This means that omega g is here, is shifted to the right. If omega z is shifted to the right and we go down, what will happen to the phase margin? The phase margin might decrease or might be unstable. In our case, it's unstable because it goes beyond the minus 180. So shifting the omega g to the right is a disadvantage. We don't like this movement because it decreases the phase margin, okay, and it might decrease it and stay positive or stable, or it might go to the other side and make it unstable. So this is the first case if we add positive gain in dB. Okay, what will happen with the next case? Next case, if we add negative gain in dB, this means that we are taking the graph downward. If we add negative gain in dB, we are taking the graph downward. And if we take it downward, this will be like the case. Okay, so what will happen? Here omega g will be here, like for example. If we go down, phase margin will increase. And this is a positive movement. So shifting omega g to the right by adding gain is a disadvantage, while shifting omega g to the left by adding negative gain, okay, is an advantage. So this is regarding the movement of the magnitude plot. Okay, let us go to the movement or shifting of the phase plot. If we add positive phase to the phase plot, then this means that we are moving it upward. If we add a positive phase, we shift it upward. Okay, and if we shift it upward, omega p will be shifted right. This is the new omega p. And if we go up and check the gain margin will be increased, and this is a positive movement. So shifting omega p to the right by adding positive gain is advantage because it increases the gain margin. This is the first part. The second part, if we add negative phase, if we add a negative phase to the phase plot, what does this mean? What's the effect? Adding a negative phase will take the graph down, and due to this fact, omega p will be shifted left. This will be our new omega p. And if omega p is shifted left, if we go upward, the gain margin will be reduced or it might be unstable. So this is disadvantage. So we have 4 cases: shifting omega g right or left, and shifted omega p right or left by adding positive or negative contribution on the gain magnitude or on the phase magnitude or in the phase plot. So this is what we are speaking about, and in order, here it's summarized. Here it's summarized. If we subtract, if we add negative gain, what will happen? Then omega G will be shifted to left because we take it down. And this will increase the phase margin, and this will be the phase lag contribution. When we design a phase lag controller, it will work on the attenuation. What does mean attenuation? That we are adding a negative gain in dB, okay, or in the normal scale it will be less than unity. K as a magnitude, the normal scale it will be less than unity, and it will be in the dB scale it will be negative. So we are interested in the design by adding a negative gain attenuation, and this will increase the phase margin, and this will be the phase controller design. Okay, while adding positive gain will shift the omega G to the right and will decrease the phase margin, and this is disadvantage. Okay, this is regarding the magnitude plot. What about the phase plot? Adding positive phase to the phase plot, will shift it up, and shifting it up will shift the omega P to the right, and this will decrease the this will increase the gain margin, and this is the contribution of the phase lead. So phase lead, it add a positive phase. As you remember, the lead controller, lead compensator, it has a positive phase. Positive phase, it will shift the phase plot upward, and correspondingly it will shift the omega P to the right, and it will increase the gain margin, and this is the lead effect. While adding a negative phase will shift omega P to the left, and this will decrease the gain margin, and this is disadvantage. So in the design process, we will be utilizing two facts. In the design of controller. We will capitalize on two things. Number one is the addition of phase to the phase plot, and this fact will shift omega P to the right and will increase the gain margin, and this is the effect of the lead controller. And the second thing that we will capitalize on is the attenuation. We will add negative magnitude in dB, or the K in normal scale will be less than unity. So we will shift the magnitude plot downward, and this will shift omega P to the left, and if omega G is shifted to the left, this means that the phase margin is increased, and this is the major effect of the lag controller. Okay, here the slope of the magnitude curve at omega P, where we calculate the gain margin, and the slope of the phase curve at omega G, it indicates the system sensitivity to changes in the due to addition of controllers. Okay, if the slope is very steep, it will have a major changes, but if the slope is small, then it will have a minor changes. Okay, those 2 points I will not discuss with you. Okay, and I will move to this section. So this section is related to the relationship between the system type and the body plot. Assume that we have a given body plot. Assume that you are provided أنا أعطيتك body plot for phase and magnitude, and especially we focus on the in this section we focus on the magnitude. We focus on the magnitude plot. Okay, and I give you a magnitude plot. Okay, so and I ask you to determine two factors. The first factor is the system type, and the second factor is the value of the gain Kp if system type is 0, Kv if system type is 1, and Ka if system type is 2. So how can we determine such thing? In order to remember, to discuss this fact, we want to remember that the error constant, they are related with system type. Okay, and for Kp, it's related to system type 0, and this is its definition. And as I discussed, Kp will be the collected gain value as I discussed in the previous lecture. So if we have a magnitude plot, and 0 system type, okay, this means that this slope will be, I discussed that it will be minus 20n, and n in our case is 0. This means that it will be 0 dB per decade, and this is a flat line. So the value above the 0 dB line, it will be not due to the system type, it will be only due to the constant gain K, and it will be only due to 20 log Kp. 20 log Kp, and from that, if this value was assumed that it's A, so we will equate it. 20 log Kp is equal to A, okay, and as shown here, the value will be 20 log K, which is equal to 20 log Kp, which is equal to A, and from that we can find Kp is equal to 10 to the power A over 20. This is for the first type, which is system type 0, and regarding Kp. Now regarding the error constant Kv, this is related to type 1, and as I mentioned, Kv is equal to K according to the previous discussion. And what does this mean? This means that the initial slope is minus 20. The initial slope of the curve is this one, minus 20 dB per decade. So from this, we know that the system type, if we see minus 20, this means that the system type is 1. Because minus 20n is equal to this slope, and n is equal to 1. So this is n we have found. And what else we want to find? We want to find the Kv. So regarding the Kv, we will have, an extension of this initial slope line. We will extend it as shown. And we have two possibilities. The first one is to find the intersection between this extension and the omega is equal to 1. Okay, and from this one we can find 20 log Kv immediately. This height will be 20 log Kv. And the other one is to extend it till it will hit the 0 dB line. And here, omega 1, we will find it. And from omega 1, we can find the Kv as given in this page. So regarding the system type 1, the initial slope will be minus 20, and the initial slope and the initial frequencies only Kv, okay, and the pole at origin will be acting. All the poles and zeros with corner frequency, they will not be effective. So this means that L of j omega at the low frequencies before any corner frequency will be 20 log Kv minus 20 log omega. We are speaking about system type 1. And in order to find the Kv, we will have the intersection between the extension of this initial slope line with the 0 dB line. And this L of j omega, okay, which is equal to this, will be equal to 0. If it hit 0 dB line, this means that the value of this extension is 0. So this means that the two components are equal, and from that we find that omega 1 is equal to kV. This is the first case. And the second case is related to the intersection of the segment or its extension with omega is equal to 1. And this is the equation. And if we pay attention, this part is equal to 0. So this means that the value will be 20 log kV. So this is regarding the second case. And regarding the third case, this third case is related to system type 2, Ka. This means that system type 2, this means that the initial slope of the magnitude curve will be minus 40. And if it is minus 40, immediately we can say that the system type is 2. Because minus 20 n is equal to 40. From that, we can find that n is equal to 2. So this means that at the initial frequencies, only Ka and the pole at origin will be acting. And this is the formula for our case. And again, in similar manner, we will have the intersection of this line or its extension with omega is equal to 1. And we will equate it to this. And at omega is equal to 1, this part will be 0. And we are left with this part, and this is why it's equal to 20 log Ka. Here, 20 log Ka. Okay, so we find its value from the graph, and we equate it with 20 log Ka, and from that we find Ka. And the other possibility is to find the intersection of the minus 40 or extinction with the 0 dB line. And if it intersects with the 0 dB line, this means that its magnitude is equal to 0. And by equating those two equations, we get this formula. Okay, this one, omega squared is equal to Ka. And this omega A, we find it from the graph, and immediately we can find Ka by squaring this value. So these are the three cases where we can find the Kv, Ka, and Kp, and we can find the system type. So from the magnitude plot, we can easily find them. So in the next section, we'll discuss few examples. I will not discuss them all. But there are some comments in the examples. So the first comment is this one. Instead of that, it's then. Okay, I will discuss the last one example, and I will correct if there are any mistakes. I will correct them. And the second mistake is this one. It's not 300. It's 30. So correct it, please. And in continuation with the comments. Okay, so this system has not 4 components. It has no 4 components, it has 3 components. Okay, and here it's some language mistake. Instead of that, the correct one is it. And if we continue, this is not 1, it's 10. Okay, and here it's not 10, it's 1. Okay, some mistakes. So this is the last example that I will discuss. Okay, all of the examples, they are described in details. Okay, and in this example, we have single 0, gain K, pole at origin. So this means that we have system type 1, simple pole, and a quadratic or complex conjugate pole. So this is the constant gain K, and we have a 0 at 10, pole at 2, pole at origin, and a complex conjugate pole with corner frequency is equal, omega n is equal to 50. And this means that zeta is equal to 0.5. We should calculate zeta in order to make sure that it's complex conjugate. If it is not complex conjugate, we should go back to real distinct roots or real repeated roots. And these are the roots, so they are complex conjugate, and we can proceed. So the system type is 1, the degree of the denominator is 4, the degree of the numerator is 2, and the lowest corner frequency is 2, and the highest is 50. So in the following sections, we will discuss, here it's discussed that the magnitude of each part of each of them. So the constant gain K, it has this 20 log 5, which is equal to 14 dB, while its phase is 0. And the 0 at omega is equal to 10. It has 0 contribution until this corner frequency 10. And then it moves with a positive 20 dB per decade, and its phase, so it's 0 till 0.1, the corner frequency, which is 1. Okay, and then from 1 to 100, it goes with plus 45 degrees per decade, and at 100 it will be plus 90 degrees. Okay, and the pole at 2. So it has 0 until this corner frequency 2, and then it drops with minus 20 dB per decade, and its phase will be 0 till 0.2, which is 0.1, the corner frequency. And then it goes to minus 90 at 10 omega C, which is 20. And after that will be constant, 90. And the pole at origin, it's a straight line with a slope of minus 20 dB per decade for all frequencies, and should pass through the 0 dB line at omega is equal to 1. And its phase is constant, is equal to minus 90. And the complex conjugate poles at corner frequency of 50, it has a magnitude of 0 till omega n, and after that it drops with minus 40 dB per decade. Okay, and its phase is 0 until 0.1, the corner frequency, which is 5, and then it drops to minus 180 degrees at 10 corner frequency, and between 5 and 500, the slope will be minus 90 degrees per decade. Okay, so regarding the magnitude plot, the gain at the lowest corner frequency will be 20 log K minus this, and it will be this value. So this is the starting value here for the overall graph. Okay, and the initial slope of the magnitude curve will be minus 20n, and it will be here, it will be minus 20 dB per decade. And the final slope, this here in this area, it will be minus 20 multiplied by n minus m, which is equal to, here it will be minus 60 dB per decade. And regarding the phase plot, the initial slope will be minus 90 degrees, and this is obvious here. This is the initial phase, minus 90 degrees. Okay, and if we go up, the final phase, after taking into consideration all of the poles, will be minus 90 n minus m, which is equal to minus 270. And this is obvious also from the overall graph. This is the overall graph, and this value is equal to minus 270. So you should practice this, and I will send to the coordinator the Similog paper. Okay, and this example, the last one example, I will send it because it's covered in more details than this. And you are required, I will send you empty paper for this example, and you are required to draw the body plot for this case. Okay, so by this chapter is over, and I wish you understand this chapter, and in the next chapter we will start with the design process. Thank you, and wish that you understand everything.